then you have a few questions in the tutorial sheet, so you can give it a try. Okay, so any question on what we discussed till now? So this concludes the chapter on flip-flops. I will want to do a bit of diodes in a few minutes. So if you have any question before we move on to that, so we have around 20 minutes before we reach 8:30. So I'm going to cover a bit on diodes now. We've covered diodes already, but then we have a chapter which is a bit more advanced diode circuits. So I will want to start that. Okay. So if there's any question on flip-flops, you can ask. Else you would attempt the questions on the tutorial sheet, and then we're going to look at these questions on next Thursday. Okay, so I'm now shifting to the next handout on diode circuits. Okay, so I've just sent this lecture series to you, so I will do that, this handout. So it's a bit more advanced diode circuit. So for your batch, we are going to consider clippers, not clampers, but you have it in your notes. If you want to read on clampers, that's fine. But for your level, you're going to for your batch, for your group, for this module, we're going to look at clippers. So clippers, basically, as the name is saying, we can shape waveforms by using diodes. Clipping means you're taking off parts of a waveform and removing that so that to create different types of waveforms from using diodes. So the simplest one, we've actually looked at it already. So I'm going to do that again. So if you have a circuit like this, for example, which we had something similar in your test. So if you're feeding a waveform like this, let's say a sinusoidal waveform of a magnitude of 15, yeah, and a given frequency not shown here. So if you feed such an input to this circuit, so VG is a generator, and you wanted to get what output would you get here? Okay. So let's look at that. I'm going to again shift to paint to just explain that again. One second, I'm just copying the waveforms to paint so that we can discuss. So this is your input waveform, which I'm copying again to paint. Okay, so now I'm just sharing a screen for paint. Okay, so this is the waveform, and we've done that in class. Just to small recap, so we can build on that. I want to progressively go to more advanced circuit. So we've seen if you have a waveform like this applied to this diode circuit. So we've seen that basically what we want to find out is for what part of an input waveform is this diode behaving in forward bias mode. This is where you will short circuit the diode if it's assumed to be ideal, and then for what part of the waveform is the diode actually reverse bias, which is when you will open circuit it. Now this one is quite straightforward. When you are in the positive half cycle there, you actually this is like positive. So this one is going to be positive, and this one is going to be negative. Yep, in the positive half cycle. So for this one, I just put a plus there. So this is your positive half cycle and your negative half cycle. Yep. So that positive half cycle, this is positive. So you can see the diode is reverse biased. So you will have an open here. So if you're opening this circuit, it means no current is flowing. You are simply measuring the supply. So in a way, if I just copy that down and show you how the output waveform will look like. Yep. So it means we're going to maintain this part. So this part would appear across your output. So if that's your output waveform, this one is showing the output waveform. Let's put that outputs. So this is your output waveform here. So we see that for the positive half cycle, since this is now reverse biased, so you're simply going to remove that, and you're measuring V naught is simply your supply because no current flow is flowing and no drop across R. So this is going to be maintained. On the other hand, when you have the negative half cycle there, it means one way you can think of this is now the polarity is reversed here. Yep. So you're having your negative here and positive here. Yep. So you can clearly see now your diode starts conducting because now you're sending current in the forward bias mode. Now, if this is in the forward bias mode, it means it is short circuited because we know a diode in forward bias mode can be assumed to be short circuited if it is ideal. So if it is short circuited, the voltage across a short circuit is simply 0. It means you would not have this segment there. This segment would not appear because the voltage would not appear. So this is what you expect to get at your output if you have such a circuit. You can see here clearly you're actually maintaining all the positive half cycles are being maintained. This is called half-wave rectification. So later down in your handout, you're going to find a section called half-wave rectification. Means we are maintaining only half of the cycles. We also have full-wave rectification. So if you use a diode bridge circuit, you can actually maintain all the half cycles because each half cycle actually corresponds to energy. Yeah. So this one is maintaining a positive half cycles only and throwing away the negative half cycles in a way you're wasting energy in a way if you want. So this is one way you can look at it. But of course, this waveform can be smoothed if you start connecting capacitors across it. So the capacitor is going to store energy in this section, and then when it's starting to drop, the capacitor is going to prevent it to stop, just like a flywheel does similar work in the mechanical system. And then when it picks up again, the capacitor charges back, and then when the output starts to drop, it will provide charge to maintain the voltage as much as possible. So this is one example of a half rectifier, which will come to that later in the same chapter, in the same handout. Now let's look at another example, second one. Just clear this one. So we're going to use paint to illustrate the waveform. So I think it's the correct platform to do that. I can show that clearly to you. So let's look at the second example, which we have. So same input waveform, but now let's consider we are connecting your diode circuit in that way. So I'm just not going to go to paint for this one because this one, and this one are pretty very similar. So I'm just going to discuss them with you, but I would go to paint for this one and this one to show how you analyze it. So a bit more difficult here because you have this battery connected here. Yeah, you have a battery connected, so we have to study that in more detail. So let's just go through this one first. So if you were to apply such a waveform to this type of circuit, let's see what happens now. So same type of analysis. If you have, let me just annotate in this one. So if you have this positive half cycle, that means this is positive, yeah, and this is negative. Okay, so you can see here this circuit is trying to send current in this direction. So your diode is forward biased. Okay, is forward biased. So you can replace that as a short circuit. It means the whole applied voltage in the positive half cycle, of course, as long as this is positive, this is negative, positive, and negative. As long as you are in the positive half cycle, you will have the current flowing, and what you measure at V naught is simply the supply. So you're going to measure this positive half cycle. You're going to measure that. Yeah, so you're measuring this thing. Now, when it comes to a negative half cycle, so now the polarity reverses, so this becomes positive here, and this is now not positive, this is negative. Okay. Okay. So in that case, okay, so now it's positive, negative. So in a way, now you're trying to send current in this direction, and you can see now your diode is reverse biased. So you would open circuit it. If you're open circuiting this one, no current is flowing across your circuit, so the voltage drop you get across the resistor is 0. It means V naught to be 0. In that case, it means this is going to be 0, and then when it's positive, it's going to pick up in the same way, and then it becomes 0. So you can see the waveform you're getting for this circuit and for this one are exactly the same. This is also doing half rectification. Yeah. So if you swap the positions of R and D, and then you of course change the sense of D, you get the same circuit here. So both waveforms we found are the same. Let's consider part C and see what waveform we get. Okay, let's consider again same approach. So if we have a positive half cycle here and a negative one here, so in the positive half cycle, this is positive and this is negative. Yeah. So if you try now to send current in this direction, this is forward bias. So you're going to short circuit this one, and you're measuring the voltage across the short circuit. So current is flowing the circuit. That's fine. But since it's a short circuit now, the voltage will be zero. So in that case, your output will be zero in that region here of your positive half cycle. When now it becomes negative half cycle, so the polarity will reverse. So now this is plus and this is minus. So it plus means now we're trying to send current in this sense. So this would be now open circuited. So no current is flowing across your circuit. The voltage drop in your resistor is zero. So all, according to Kirchhoff's voltage law, all the applied voltage should be appearing across the open terminals, which we are showing your diode is represented. So you are open circuiting your diode. So the voltage V naught is simply equal to Vg, but since it's negative, it will still be a negative like this. So this is what you're getting at the output. Okay. Yep. So you should be able to use Kappa analysis. We've done that, but we are considering different variations here. Now, next one we consider is part D. So part D, as you can see here, you are connecting your diode here and you're measuring your output voltage across the resistor. So in the positive half cycle, I annotate again. So in your positive half cycle, this is going to be plus and minus. So clearly now you're trying to send current in this sense. So this is now can be represented as an open circuit. So no current flows in your circuit. Your output voltage will be zero. So in the positive half cycle, you get a zero output voltage. And now when you would go for the negative half cycle, so this becomes positive here and negative here. Now you're trying to send current in this sense. So your diode is forward biased. So you can replace it as a short circuit. The whole voltage would appear across your resistor because it's a short circuit. So you're measuring basically the negative half cycle. So in a way, again, same comment we've done earlier. The waveform you're getting for this one and this one are exactly the same. These two is exactly the same. So you're going to get the negative half cycle. Now, what I'm going to do now, I'm going to shift to paint to explain to you how we analyze a circuit like this, where we are putting actually a battery here and see how we're measuring the output is across a diode and the battery both. Yeah, so that's important for us to analyze. Now, if you look at your notes, if you go down, I've taken some examples here. I'm going to explain in detail how to solve for this, but I'm going to do that now so that you have a foundation for that, and then you can go on and read the notes and be able to understand what's there. So let's take one of them, and then the remaining ones I'm sure you'll be able to go. Okay, so I'm going just to copy that into Paint. Let me copy the circuit first. And the waveform. Okay, so let's look at this one. Now, first thing you can see your, let me just share the screen. Sorry, I'm going to share the screen for Paint. Sure. Okay, you should be able to see it now. Okay, now let's first see how your input waveform is changing. It's changing from 15 volts here to minus 15. That's the first thing. Now, to analyze this type of circuit where you have a battery, one trick you can use is you can assume that this one here is always at 0 volts. So this terminal here is always at 0 volts. That's one trick which works very well. And then let's say in this range here, in this positive half cycle here, it is let's say 15 volts. Then what's happening here is this terminal here is becoming 15 volts. Yep. This is why you get, let's say, 15 volts or any other value which is positive here in this positive half cycle. It's just that this one is 0 volts and then this is 15 volts. If you take a difference of the two, you're going to get to plus 15 volts. That's okay. Now, what happens when your waveform is becoming negative? Let's set minus 15 volts. Typically, one way you can look at that is say, yes, this line here is becoming 15 volts, and then the top one is 0 volts, so it reverses polarity, and then you can say, yes, this is because below here is 15 and on top it's 0, then you get minus 15. Another way to look at it is you can put the minus 15 here itself. So you're always saying that this terminal here is at 0 volts, and then it's upper terminal which is changing polarity, is just changing the value. So if this is plus 15, so the upper terminal here is plus 15. If it's minus 15, so this actually becomes minus 15. It's exactly the same as you're reversing, you're putting the 15 volts down here and the 0 volts there, because the difference is still minus 15. Okay, so let's take this approach here where we are assuming that this terminal here at the lower end is always grounded at 0 volts, and as a waveform is having different values as you go along the sinusoidal waveform, it's the magnitude of the upper terminal which is changing. It could be plus, it could be minus, depending on where you are on the waveform. That's an important approach to solve this type of problem. Now, next thing we do is, once we assume this is at 0 volts, as you go across this battery, you would see that we are going from, so this is going to be the plus terminal, and this is going to be the minus terminal. If you follow the way I'm doing now, you will never get any problem to analyze the circuit. Yeah, so pay close attention to what I'm doing. So as we go from this terminal here to this one, you will see that this terminal is we are going from 0, and then we go from minus to plus. It means this point there, at this point, show it. So this point here, on one side of your, at this point here, so we actually have plus 10 volts. For the simple reason that you are moving from minus to plus. Yeah, if you look at the way your battery is connected, if this is assumed to be 0 volts always, and then you are now changing from a minus to positive, means the terminal here will be at plus 10 volts. Yeah, because it's 0, and then you're adding 10. It's going moving from minus to plus. So this is plus 10 volts. Now this becomes very simple now. Once you have set the terminal of one of your diodes, then it's very simple. This diode here is forward biased. If this node here is above 10 volts, because this is the anode and this is cathode, so as long as this terminal here is above 10 volts, your diode is forward biased. So let me write this down. What we've concluded is your diode is forward biased when the voltage that you have, when your voltage is above 10 volts. Okay, let me explain that again. So based on the approach we're using here, we are fixing this at 0 volts. As we go across the battery here, yep, so we are changing here from minus to plus, so 0 plus 10, we get plus 10 volts here. Now, how does the diode behave? We have here's the anode. So if the anode that you have here is above 10 volts, it is forward biased. And similarly, the diode would be reverse biased when the voltage is less than 10 volts. Because in this type of circuit, like we've done earlier, you would have to identify when the diode is forward biased and when it is reverse biased. So when this point is actually 10 volts and above, the diode will conduct. When this voltage here is below 10 volts, the current will try to flow from high to low, and it's going to be reverse biased. Okay. Now, it means I'm just going to draw now the output waveform. I'm just going to copy this down. Okay, and this one is going to be going out. Now, what we find is we've said that 10 volts is an important parameter, it's called a threshold. So above 10 volts, it is forward bias, and below 10 volts is reverse bias. It means you would need to draw a line on your input waveform, which is 10 volts. Because this is the boundary between the diode going from reverse bias or forward bias. So it's a very important threshold. So you're going to draw this line there on your waveform. This is a 10 volts line. Yep. And then next step here, you're going to draw drop down lines like this. I'm just going to do that in thinner lines. So these are important points because this is where your circuit is shifting from one state to the other, because the diode would conduct or not conduct. Now the next question is to identify when the diode is forward biased, what are you measuring, and when it's reverse biased, what are you measuring? So let's look at that. So we've said here your diode is forward biased when voltage, applied voltage, is more than 10 volts. So it is that region there. This is where your diode is. Here your diode is, if I just draw, I just write it here. So your diode is forward biased here. When it's in this region here below 10 volts, so when it's in here, your diode will be reverse biased. And next question is, when it's forward biased, we know that we can replace this diode here by a short circuit. Imagine you replace that by short circuit. So I'm just going to just take this out and put it back later. So let's take this out. So let's just take this out for the time being. And we are saying in that region here, when it's above 10 volts, you are simply short circuiting it because it is forward biased. Yeah. So question now is, if you short circuit this part, what is V naught? V naught is simply 10 volts. You're simply measuring the battery voltage, which is 10 volts. So it means in this region here, you would measure 10 volts. You would measure 10 volts. Okay. So you would not be measuring this part there. As soon as it is above 15 volts, your diode is forward biased. So you're removing this part. That's important. So yeah, as you can see here, this diode, this circuit is clipping. It's clipping part of a circuit. Now the next thing you have to do is, when the diode is reverse biased, means in this part here, this section here and this section. So what are you actually measuring? Now when the diode is reverse biased, we know that we can replace the diode by N. You can replace the diode by this circuit like this. We can replace it by open circuit. Okay. Now question for us is, if you have a circuit like this and you are open circuiting this one, if you measure a voltage across this terminal here with a battery included, what actually you measure? In this case here, obviously no current is flowing across your resistor, so there's no drop across it. That's just one important point. Now what actually are you measuring? This is your supply. So this is one terminal here, but this terminal here is not at zero. Yeah, this terminal is this terminal is at zero, but this one here at the diode is just plus 10 volts. But as you can see, your output voltage which you're measuring is across both the battery. Yeah, so you're including the battery there. So basically you're measuring the voltage across this terminal and this terminal here. So basically that's your VG. Yeah, so it means in that segment here, you're simply measuring your VG. So it's going to be here VG, and then that's your VG. So this is what you're going to get as your output waveform. Yeah, be careful. You're not measuring V naught at this point across the diode only. You're measuring it across the battery also. If you are measuring your output at this point here, then basically this will be at plus 10 volts. So you need to subtract 10 volts from your waveform. Yeah, but here you're measuring it across these two terminals there. So these two terminals is simply your VG. Yeah, it's important to know where you're measuring your V naught. So whenever you place a battery, I'm just shifting back to your handout. Yeah. So whenever you have circuits, there is batteries. So I would recommend that you always put the lower node at 0 volts, and then you try to work out one of the polarity, one of the potential of your diode. In that case, if that's 0 here, it becomes plus 10 here. And then once this is plus 10, it means 10 volts become a threshold. In this case here, when your other side of your diode, which is actually the fluctuating magnitude of your input waveform, when this one exceeds 10 volts now, your diode will forward bias, so you can replace that as a short circuit. Then what are we measuring? V naught is simply 10 volts. The remaining, of course, drop from your waveform is going to appear across R because current is flowing. On the other hand, if you say this is 10 volts and the voltage on this side is below 10 volts, then your diode will be reverse biased. So this is going to be open, And in this case, your V node will be simply your supply. So if you follow a similar approach here, let's consider this one. So I'm just giving you directions so you can try to work it on your own. So again, if you assume this is 0 volts now, but just look at how your battery is connected now. It is connected so that this is plus and minus. So as you go from 0 and you go across the battery, now this will be at minus 10 volts because you're going from plus to minus. You're reducing in potential. So this is 0 volts. So this terminal here, the cathode of your diode is going to be at minus 10 volts. So once you get this minus 10 volts, become a threshold in your analysis. This diode will forward bias whenever this terminal here is above minus 10 volts. So if it is minus 9 volts, minus 8 volts, and so on, so it means on your waveform you would have a minus 10 volts threshold there. As long as it's above that, your diode is forward biased. If it is forward biased, you're measuring minus 10. So it's going to cut at minus 10. And then when it's now below minus 10, so this again, imagine this is minus 10, and then this is at minus 11. So this is going to try to conduct in the reverse direction. So this diode will be open circuited. So this is an open circuit. Again, you're measuring the output voltage across this point and this point. So you'll be measuring your supply. So you're just going to get a small. So you get a minus 10 here, and then a small cut like this, and then a small minus 10 again. So as long as your diode is forward biased, means your voltage of your supply is above minus 10 volts, you would be getting that minus 10 volts at your output. Okay, so I've tried to explain this approach of analyzing this type of circuit with batteries. There are much more examples given here. So this one is elaborately explained there. So I would invite you to read that on your own. It's very clearly explained. I just did this one for you. And the second example is given now where you are connecting your battery in that side here. So you can do a similar analysis. Just read through the detailed explanation I've given and try to see if you can figure this out. And then you have some examples for you to try on your own and send it to a sheet, which I will also send where you have more examples to try. Okay. Now, for your case, clampers is not covered, like I said at the start. So this one you can read just for information purpose. This is not covered in your in this module, Rec 2110. So just here for information. So in the next session, next video I'll be sending out, I'll be covering xenon diodes. Yeah. So just to go through, so we're going to do xenon diodes, a special type of diode which is normally operated in reverse bias mode. So we're going to explain that in more detail. And then we've covered that today partly. So we mentioned about single phase half rectifier. So you're maintaining only half of a cycle. So it's called half rectifier. So some calculations there which you can look at. And then we have, of course, you won't be covering all these detailed calculations for your module. This is more for electrical people, but again, it's there if you want to read through. So these detailed derivations here, efficiency and these calculations there are not very relevant for you. Yeah, just you have to be able to find the waveform. So this waveform there, and later we're going to see how we actually find the try to rectify it, means try to smooth it out. So we're going to do that later. And then we'll go also for full wave rectifier. So here we have 4 diodes. Maybe you studied that in physics or any other module. Yeah. So if you connect your 4 diodes in that way, you achieve full rectification. Means you are maintaining all your cycles. You're just converting them on a positive side. So this negative cycle is converted to positive side, but you're not throwing away any of your half cycles. This is a second circuit which you can use if you have a center tap transformer. Okay. Now, next section, once you are doing half rectification, how can you smooth it out? So basically, you want to do that. This is a half rectified signal. If you connect a capacitor that way, so when the voltage starts trying to fall, your capacitor would have charge here, so it actually maintains the voltage in this way. So you don't allow it to go 0. And then at this point where your voltage across your capacitor is higher, so it starts charging the capacitor back. And again, when the voltage tries to drop across your load loop, it's going to discharge and maintain the waveform. This is what you get at the output. You can do a similar thing for a full wave rectifier. Yep. So you're going to here to achieve much less ripples because you don't in a half rectified circuit, you are missing this, if you want, this half cycle, so your voltage can drop to a very low level, a lower level rather. whereas in a full rectifier, that voltage drop is less here. So it means it's going to be less rough or more smoother, so you can very easily smooth the signal better. In a way, this means that if you have a half rectifier, you would need a bigger capacitor here, because the capacitor needs to store loss of charge so that it can provide the voltage for a longer amount of time. Whereas in a full rectifier, since you have all your half cycles are maintained, your capacitor doesn't need to be that large. Yeah. This diagram here is showing all the different steps. So typically you can use a transformer to step up or down your voltage, and then do the rectification, be it full wave or half wave. And then you can use the filtering. The filtering is exactly what you just seen with capacitor. And then a regulator is, once you study what a Zener diode is, you understand what a regulator actually does. You're going to obtain a very now steady output without any ripples. You can see here you have some ripples. So if you connect a Zener diode at the output of such, let's say at VL here, you connect a Zener diode, so you can obtain a very regularized DC like this. And then once you have a DC, you can use a voltage divider to further set the voltage level you want. For example, if that's at 10 volts, if you want to obtain 5 volts, you can use a voltage divider. Now, what you're seeing here is basically what you have in your adapter at home. So you have 230 volts AC coming in. You can step it down using a transformer, and then in your adapter, you have the rectification, filtering, voltage regulator, so that at the output that you have, be it for your laptop or for your mobile phone charger, you're getting a DC signal which is very steady. This is what you would typically find in an adapter circuit. Yeah. So I'll be sending out the notes to you. You can read on them, and then it's basically, once you've understood the previous topics, you can very easily understand all the different topics. Okay. So I'm stopping this session here. Yeah. So I'll be sending out the recorded session to you, so you can look at it again, hear it back, and then with your handouts, you can understand better. Okay. So I thank you for attention. So I'm stopping here.